Next slide. Now we move to what shapes the surfaces of the terrestrial planets: impact cratering, volcanism, erosion, and tectonics. These agents also act on the surfaces of the large moons of the Jovian planets. Let's look at something that happens for any body with a solid surface, whether there's internal heat or not: impact cratering. There are still small chunks of rock orbiting the sun left over from the formation of the solar system. Some of them have orbits that cross the orbits of the planets and moons. When they get close enough to a planet or moon, they will be pulled in by the large body's gravity and strike the surface at a speed of at least the escape velocity of the planet or moon, i.e., faster than a bullet. At such speeds, the projectile explodes on impact and carves out a round bowl-shaped depression on the surface. The kinetic energy of the impacting meteorite or asteroid is converted into heat, sound, and mechanical energy. The projectile explodes on impact. The explosion is what carves out the craters, so almost all craters are round. Otherwise, the great majority would be oblong in shape. The rock on the surface of the planet or moon is bent backward, upward, and outward, so the amount of material ejected is much larger than the projectile. For example, the projectile that made Meteor Crater in Arizona was about 45 meters across, but the crater is about 1,200 meters across, or more than 25 times the size of the projectile. The number of craters per unit area on a surface can be used to determine an approximate age for the planet or moon surface if there is no erosion. The longer the surface has been exposed to space, the more craters it will have. If you know how frequently craters of a given size are created on a planet or moon, you can just count up the number of craters per unit area. This assumes, of course, that the cratering rate has been fairly constant for the last few billion years. We now know through radioactive dating of rocks from Earth and the moon that there was a time of a lot of bombardment in the early solar system, and today is, fortunately, much quieter. At a minimum, crater age dating can tell you the relative ages of the surfaces, which surface is older than another. Careful studies of how the craters overlap other craters and other features can be used to develop a history or sequence of the bombardment on the moons and planets. Geologically dead worlds will have more craters. If you see a smooth surface, then there has been something that has erased the craters. Volcanism is any eruption of molten lava onto the surface. The molten rock has a lower density than solid rock, so it rises. Also, the pressure from the surrounding solid rock squeezes the molten rock upward. Molten rock contains trapped gases that expand as it rises, causing it to rise even faster. The structures that result from erupting lava depend on the thickness and density of the lava. I'm going to group the various types of volcanic eruptions into three basic groups. Stratovolcanoes, also called composite volcanoes, are made from very thick, low-density lava, so it can make steep sides. The lava does not flow as far as the other two types, so their diameters are not as great as the other types. They are common on the Earth. The pancake domes on Venus may be considered a type of stratovolcano, but their shapes are much more cylindrical without a peak. The Cascade volcanoes in Oregon and Washington are stratovolcanoes. Shield volcanoes are made from thinner, higher density material called basalt, and these volcanoes are much wider in diameter with very shallow slopes. These types of volcanoes are found throughout the solar system. The Hawaiian Islands are one famous example on Earth, and from their base on the ocean floor to their summit, Mauna Kea and Mauna Loa are actually taller than Mount Everest. But they are dwarfed by the large shield volcanoes on Mars, especially Olympus Mons, the tallest mountain in the solar system. And it's so wide that it would cover up most of Texas. Lava plains are made from the thinnest, lowest viscosity, runniest basalt. They cover over other features on many places in our solar system. This picture shows the Three Devils Grade in mid-Moses Coulee in the Columbia basalt flow of eastern Washington and Oregon. Several different flows are visible that occurred between 15.6 million and 14.5 million years ago. The dark mare on the moon are another example. Volcanism also adds gases to a planet's atmosphere, either explosively during a volcanic eruption such as Mount St. Helens in Washington or Mount Pinatubo in the Philippines, shown here, or more quietly as in the volcanic vents in Hawaii and Yellowstone in Wyoming. This outgassing is what created the terrestrial planet's current atmospheres. Earth's has undergone further significant processing through the action of life. Tectonics is any stretching or compression of the lithosphere. Usually tectonic activity is due to convection in the mantle below the lithosphere, but it can occur when a especially massive landform, such as a volcano, makes the lithosphere under it buckle from its weight, or a rising plume of extra hot material in the mantle pushes on the lithosphere overhead to make a bulge, such as corona features on Venus and possibly the Tharsis bulge on Mars, though that one may be due to mantle convection long ago. This picture of Mercury's surface shows a combination of impact cratering, lava plains, and tectonics. The arrows point to high cliffs up to 3 kilometers or 2 miles high called lobate scarps, running for hundreds of kilometers that are probably the result of the shrinking of Mercury as it cooled from its formation. Recall that Mercury has the proportionally largest metallic core of the planets. As the metallic core cooled, it shrank, and the mantle and brittle crust would have had to shrink too, crinkling in the process. Surface rock fractured, causing blocks of crust to thrust over others along great faults. In another lecture, I'll talk about a special type of tectonic activity unique to Earth in our solar system called plate tectonics. But remember that other planets do have tectonics. Erosion is the breaking down or building up of geological structures and transporting of material, rock for our purposes here, by ice, liquid, and wind. Water ice in the form of glaciers carves out bowl-shaped valleys such as Yosemite in California and those in Glacier National Park in Montana. Glacial moraines form from gravel transported by glaciers. The gravel comes from the glacier scraping rock, and it gathers along the side, lateral moraines, and front, terminal moraine, of the glacier. Walawa Lake in the northeastern corner of Oregon is a textbook example of a lake formed when a dam is created as a glacier recedes. Flowing liquid water on the earth is carved through layer upon layer of rocks to produce such spectacular things as the Grand Canyon on Earth. Valleys carved by liquid water have much sharper V-shaped structures than glacial valleys. Erosion by liquid water on Mars in the past is responsible for river drainage channels, but the sublimation of carbon dioxide on the walls of impact craters can produce gullies. The northern California coast near Wilson Creek, shown here, is continually pounded by the ocean. Titan has liquid methane eroding its surface. Wind picks up small sand particles on a planet's surface and strikes it against a hard surface to chip pieces of it away to make more sand. The winds can also shape hills of sand into sand dunes, as seen on the Earth, Mars, and Titan. The Titan rock is actually super cold frozen water, so the sand is chips of water ice. Besides chipping away at mountains and other rises in the land, bit by bit, erosion can also add to the formations by depositing sediments when liquid slows down enough for the suspended sediments to sink to the stream or riverbed, such as the Mississippi River Delta and the Lena River Delta in Russia, shown here. Fossilized river deltas are seen on Mars, with the one in Jezero crater being one example.